Assalamualaikum and good day. We meet again in our second class. And before we start, I would like to inform you that we are going to complete our lecture in the first half of the semester. Since if based on the schedule given by the USM authority, you can come back. You can come back from you can come back into the school at the second half of the semester. So what we can do during that time, actually we can uh, fully focus on your lab session, including the lecture time, okay, Monday 10 to 12. So it means that you are going to have three, since you are going to do the lab individual, okay, because they don't allow you to do in group. Okay, each bench only can have only one student to do the lab. So it means that even during your mini project, your hands-on also all will be individual. So we need to have all these three sessions, including the lecture for lab. So that's why we are required to complete the lecture during the first half of the semester. Okay, so the next topic that we are going to discuss is RISC. Okay, RISC. So what is RISC? If we talk about ARM processor, then we are related to the RISC. And before this, that we have studied about microprocessor Intel and microcontroller Intel 8051 and 8086. They are all about CISC. And these ARM processors are we call RISC. And these are two kinds of architecture, and we are focusing on the software part. Software architecture, we have two kinds. One is CISC, the one that we have discussed. We have discussed this last semester, okay, in the interpretation. And now is RISC, the second architecture of the software. So RISC stands for Reduced Instruction Set Computing. Okay, and CISC is the complex instruction set computing. Okay, reduced instruction set computings. Computings, actually, it's not computer, computings. Okay, microprocessor. Okay, also it is considered as a kind of architecture to the microprocessor. We use the RISC, so this is one kind of architecture for the microprocessor that we use RISC, where it designed to perform a set of smaller computer instructions so that it can operate at a high speed. So it means that the instruction is reduced, okay, compared to the CISC. RISC means that it has less instruction. Less instruction doesn't mean that it cannot do anything that going to be less than CISC. No, it means that you are doing more more tasks in a single instruction. Okay, you are doing more tasks in a single instruction. You only abbreviation RISC refer to is the instruction is reduced. You have less instruction. Okay, so what we will cover about RISC, I think this is a short topic. Nevertheless, we are going to have a quiz for this uh, quiz or assignment. I'm not sure yet. I'm kind of confused yet. But by uh, end of this recording session, we are going to have a assignment for this. Okay, we are going to cover history, theoretical about the risk, and then we have the advantages. Actually, there are advantages and disadvantages between the SIS and the RISC. Maybe we are going to have assignment for you to discover if here we are discussing about the advantages, then we need to know about what is the disadvantages for this overseas. And pipelining is the other new kind of technology which being implement in in the RISC, so it must more make the processor become more fast. Okay, as you know that there are two kind of making the processor become more fast every years. Okay, it's not about the material that we develop the microprocessor because from more than a century ago, the silicon is being used, and we don't have any other material which can be upgraded, make the electron which can move faster, or any material that can make the processor become more faster. So there are two kind of what we call two kind of way where the manufacturer of the microprocessor claim that the processor become more faster. One of it is by reducing the size of the microprocessor. So once it reduces the size, means the electron that travel through the hardware is less. If the traveling of the electron less, means that it become more fast. Okay? And the other way is to implement a new technology. Okay, one of it is the pipeline. Okay, when you have a pipeline, means that you can process instruction more faster. Okay, before the SIS era, compiler were hard to build. Compiler, the one that we use to compile whatever assembly code that you write, it will compile to the machine. Hard to build, especially for machine with registers. Okay, because the SIS is all about registers. Means that it didn't involve any memory to register transfer. It make machine do more work than software. Okay, during last time, make the machine do more work. Okay, the task for the machine, the hardware itself is more than the software. Have instruction that load and store directly to memory. Okay, memory to memory operation. So that's why it become more, I mean, how more time for execution required. So, before there is also the software were rising and the hardware costs were dropping. Once the requirement for the software is high, make it the cost is rise. Okay? And at the same time, the hardware will drop more as much functionality to hardware. We are depending on the hardware. Magnetic core memory was used as main memory, which was low and expensive. As you know, during that time when you use this, you can have an instruction where you can transfer from memory to the register. But in this, most of the RISC, okay, especially in ARM, the one that we are going to cover this semester, they don't have the instruction to process between the memory and register. Okay, the only thing is you can it didn't mean that you cannot use the memory. The only thing it didn't process it. If you want to add, if you want, there will be no such instruction that you can add from a certain memory to a register. No, the only things that being used by is being used in memory is you want to load to memory. Okay, you want to store to the memory. But the other instruction, if you want to process it, it only can be done through register. So that's why they increase the number of general purpose register. Even though you know exactly there are 1,000, maybe a million of register inside the processor. But the general purpose, the one that can be accessed by the programmer, is limited, and it is higher than the SIS microprocessor. Okay, where complex instruction set computing, okay, use complex instruction, for example, multiple add, where you can multiple add the memory with the register and some others. Okay, where the technology was advancing, as I mentioned, one way of advancing the technology is make the processor become more fast is uh, sorry, this is about compiler. Okay, you make the compiler, you improve the compiler. Means that the simple compiler found it difficult to use more complex instruction. Okay, optimizing compiler really needed more powerful instruction. Optimizing compiler really needed more powerful instruction. Cache is one of the memory, and it was inside the microprocessor, where it allowed the main memory to be accessed at similar speed to the control memory. Okay, since the cache, the memory is built by the solid state also, it's not like magnetic like other kind of memory. So the speed to access it become more faster. Semiconductor memory was replacing magnetic core memory, okay, which reduced the performance gap between the control and the main memory. if you can make the control and the main memory using the same technology, which can be accessed very fast, okay, then you can have the advancement of the technology. You make the system, microsystem much more faster. Okay, inception of RISC. Okay, actually, okay, this is stated by the by the John Cobb IBM at 1974. Okay, even you also are not exist in the world, and I'm only just a few years old. Okay, it proves that 80% of the work was done using only 20% of the instruction. Okay, only 20% of the instruction. During this time, it means that the processor, the microprocessor system is depending on the hardware compared to the software. Okay, there was three RISC project during that time. IBM 801 machine. It was at 1974. Berkeley's okay is the one that the first introducing the RISC. Okay, RISC 1 and RISC 2 processor, which is at 9080, and Stanford MIP processor million instruction per second at 1981, where at 1980 announcement of the first commercial RISC chip, it is being used commercially at 1986. This is about the history. Okay, what is the difference between RISC and SIS? Where RISC use only simple instruction that can be executed within one clock cycle. That is the key point. You can execute only one clock cycle. You require only one clock cycle. Okay, sorry for the unforeseen circumstances. Okay, we carry on. As we know that use only simple instruction per executed within one clock cycle. And the difference between the SIS and RISC, it will require one clock cycle in order to execute one instruction, which means that it use only fewer transistors for instruction, and it use more register. RISC require more registers. Okay, and it is used pipelining. Okay, what we mean by pipelining? Pipelining is uh, by introducing the pipelining, it means that the processor become more fast. Register to register operation, as I mentioned, this is the one of the unique criteria. It didn't involve the memory. Okay, where the operand is reused and the reduction of load and store. Okay, load and store to the memory. Okay, you reduce it. It use to execute the instruction between the register and register. Okay, this is actually the pipelining. What we mean the terminology of the pipelining. Okay, in comparison, we have two. If we say about pipelining, so the contrast with it is sequential. Sequential, what we mean by sequential? If you look here, we have five operations. Okay, instruction fetch, instruction decode, operand fetch, operand execution, and operation store. Okay, you are required these all operation in order to complete executing one instruction. So in this case, for example, you require how many? One, two, three, four, five clock cycle in order to complete it. And after you complete it, then you can start to fetch. I have fetch the next instruction. You need to complete the whole instruction, and then you can start with the second one and continuously. But in the pipelining, at the same time, uh, at the first cycle, this is based on the time. In the first cycle, while you are fetching the first instruction, at the second cycle, you are decode the instruction. Okay, you can see clearly. It is actually ID. Okay, you are decode the first instruction. At the same time, also you are fetching the second instruction. You are doing it simultaneously. At the third cycle, for the first instruction to be fetched, okay, operand to be fetched, OF, while the second instruction is being decoded, and you can execute also the third one where you fetch the third instruction, and so on. And currently, I've been informed that there are up to 17 pipelines in the current processor. So the more pipeline that you available in the certain processor means that the more instruction to be executed within one clock cycle. Okay, the only concern is about when we have branch. Okay, for example, we have jump instruction or conditional instruction where you can execute on sequence, you need to go somewhere else. Okay, that will be a concern. And it is not take the advantage of pipelining in order to execute faster. Okay, maybe I'm going to put this as later on as your assignment. Okay, data dependency can be addressed by reordering the instruction when possible. Okay, is by compiler. Actually, you need to choose. Okay, this is quite, for you to understand is by doing the examples. Okay, what it means that okay, data dependency can be addressed by reordering the instruction when possible. Okay, this is to avoid the branch. Performance degradation from the branch can be reduced by branch prediction or executing instruction for both branches until the correct branch is identified. Okay, this is the way to make also while you are having a branch. You can make it to execute it parallel synchronous. And then at the other time, then it will identify which branch it should be executed. Okay, there are other also advantages, risk overseas, where the new processor can be developed and tested more quickly. It being less complicated is one of its aim. Okay, smaller instruction set are easier for compiler programmers to use. Okay, the use of the RISC today. If you know that 8086 is the architecture which being used until today for the desktop, okay, and only the that retains architecture, uses sys architecture, where the large base of proprietary PC application were written in x86 or compiled into C code. Intel was able to spend vast amount of money on the processor development to offset these advantages enough to maintain the PC market share. Okay, this is about history. There are a lot of uh, history regarding this and sees how it been compete between each other. Okay, sys and RISC architecture are nearly indistinguishable, means that sys processors are used pipelining and can be complete multiple instructions per cycle, where the transistor technology has allowed more room on chip, allowing RISC to have more sys like instructions. Okay, there are a lot of other risks and sys advantages and disadvantages which I not cover in this session. Maybe later on during our discussion in detail about the ARM processor, we are going to realize that concept. Okay, thank you.